So we're back for the second half of this presentation about, science, hypothesis, theory, all those kinds of things. So I just wanted to drop back here and show you one thing in particular, which I mentioned in the previous video, and that was that you can find from the Global Monitoring Laboratory, which is in Boulder, Colorado, or just outside of Boulder, something like that, that they're posting about the parts per million of CO2 in the atmosphere. And you see here it's 413, nearly 414 parts per million. And we haven't seen that, by the way, in ice records. We haven't seen that kind of concentration ever in the history of Earth that we have studied through measurable things like ice core samples that hold gas, if you don't know, or compressed ice from snow and so forth. You can look back into it, and we've never seen the atmosphere that high. All of this is to say, again, this is something we're building over the semester so that we can understand this. So your textbook looks here at what are the steps in the scientific process. What's the method itself? I wanted to expound upon that a bit when you look here at it. So this one's in your textbook, but this is the one I want to look at because it also involves publications. And so when we look at observations, asking a good question, that is one that can be tested, and leading to, what is your question that leads to your hypothesis that comes with predictions about what we would expect to find in a thing. You test it, and does it yield a result? And if it doesn't fit, you go back again. If it to reject the hypothesis and it has to be something else, then okay, we go back to the drawing board. But the idea here is it's a circular kind of thing until we can establish our results. And then what happens? It goes into you submit the paper for publication to whatever journal that you want to send it to. It's a scientific paper. Well, they're not just going to put it on the printing presses. They're going to put people that have also published in this field and know what they're reading to challenge the methodology or the data or whatever else came about from the study. And if they reject it, then you go back to the board, you or your team or whomever made this, you go back and see what's wrong and go through it again. If it is accepted, then it goes to publication in a scientific journal. And all this feeds upon others reading this and doing their own research. And I've often talked about anthropogenic global warming, that is, humans are driving this. I often see the people challenge this and say, well, gosh, why don't they publish the scientists who say that global warming is all natural, and not human driven? And that would be like saying, guys, why don't we teach ABCs in college? Because it's saying the same thing. It's like, well, it's not in dispute anymore. You'd say, well, those scientists think it is. Well, look at why they're not being published. And it's not from a political standpoint. It's from absolutely a scientific standpoint. And so, again, understanding what is eventually acceptable in truth with a scientific theory is it repeatedly passing test after test after test, never yielding necessarily a wrong answer, but somewhere in the vicinity of right, and the strength of that being somewhere like 95, 96, 97, 98% factual. Again, with science becoming a theory. Again, you can't see plate tectonics necessarily, or evolution, or gravity for that matter, but we know it is a reality. So I just wanted to point those things out to you and how important the peer review process is, okay? So when you look at the IPCC, the Intergovernmental Panel on Climate Change, sorry about that, it's a mouthful. When they produce these things, it is an army of scientists that are gathering and so many different fields, information that gets published, okay? So when it finally hits publication, you're looking at a cross-section of people that may or may not find that useful or interesting depending on what field they're looking into. So I wanted to share this with you. I'm not going to play the video. I hope you'll go find it, okay? But in 4 minutes, this person, her name is Rachel Pike. This was posted over, 10 years ago. but she's telling you in 4 short minutes how you get to a news headline which tells about some discovery, which usually, I swear, when I see it on the news, it's almost funny. You laugh at it because you're, without any context, it kind of falls into that area of junk science because it's a headline. It's necessarily vague. What it's supposed to be, though, is a trigger for you to go, oh, that sounds interesting. Let me go look at it. But again, in this era of hoaxes and false news and all these other kinds of things, this renders you as a person in the general public, typically, you don't know what to believe, so you just throw your hands up, and that's not what we're trying to do here. Not at least in my class. I want you to follow these things down. I want you to look at them. I want you to try to understand them. I don't understand them all. I came from a background, my previous job as an environmental scientist, I still don't know climate change. I never had stuff like that, so I'm doing it myself. But that said, I can't just up and throw my hands up and say, well, that's all for the scientists to do. No, your job here is as a thinking, rational adult heading for a college education is to deeply delve on, critically reading, critically writing, critically questioning sources and coming to your own understanding of it, but also appreciating what these people have spent a lifetime trying to put together here, and you shouldn't throw it away like it's a snowball, because I often see this gentleman right here, James Inhofe, senator from Oklahoma. He's walked on that House floor, or the Senate floor, and he's brought his little snowball to prove that global warming isn't happening because, well, it's cold outside. Yeah, that's called winter, and that's called weather. I'm talking about climate. Climate and weather are two different things. An amalgam of weather, day after day, year after year, that becomes climate on an average for a place. So don't bring weather into the discussion to prove your point that climate change isn't really a thing, and that if it were, humans didn't have anything to do with it. All right, moving on. How do we measure some of this stuff? How do we model it? How do we recreate climates of old? And what you do with these models, like with weather, when you see I got to tell you this, we're not going to get to take a tour of the National Weather Service at Old Hickory, but I'll try to share some videos with you about it if I can this semester. But those guys, over the years that I've been taking my students through there, have shown us that just in the last couple of years, with the ability of their weather models, they're able to predict more accurate 7-day forecasts now than just a handful of years ago they could do on a 3-day forecast. Okay, so predicting snow in an area for Nashville, mind you, it covers a huge area. So if it snows somewhere within that area, that's a spot on weather forecast. So how are they doing this, though? They're pouring in all the data that they have about temperature and humidity and air pressure and winds and all these things, and they let the scenarios run with the model, and they'll typically take the 3 most often selected forecasts that come out, look at it, and then put their tweak to it. Okay? So weather models are really good, and believe it or not, the European model works best for the United States. Nobody really knows what it is about it because, but I've been told that any number of times. So that's the one they often go to and report from. Okay. As we look at closed and open systems here, this is addressed in your textbook. Please look at it though. Open to energy, for instance, but is matter coming from outer space in any kind of abundance? Can we expect a coal-bearing meteor to come on in and help replenish our fossil fuels? No. So that's closed to matter, even though the energy of the sun can go in and out. So look at the difference between open and closed systems and understand what a dynamic equilibrium is. An equilibrium is one that is in balance. It may tip one way or the other. I often talk about it like foxes and hares. When there's an abundance of hares, obviously there's not enough foxes. They'll have kits. They'll have, the cubs will, come to be adults, and they'll eat more of those rabbits. And as the food source goes down, what happens with, the rabbits go down, and then eventually the numbers of the foxes will go down. So it shifts over time, from predator and prey. But overall, in the same way you saw about CO2 concentrations in the atmosphere, it may vacillate up and down, but overall the trend will stay fairly equal if all things remain the same. So if we look at something like a positive feedback loop, which does what? It enhances the change. So if we look at an external forcing, say surface temperature, which affects ability of air to hold moisture, here's the deal. The warmer an air mass, the more capability it has of holding water vapor, okay? That would increase then evaporation to atmospheric water vapor, to greenhouse gas effect, and so forth. So this positive feedback loop keeps feeding again and changing the system, getting warmer and warmer. Now we do see something like a negative feedback loop, which would countermand what that change would be. And that the difference here is looking at the clouds. Okay, so what do clouds do? Well, clouds do in fact increase the albedo and reflect solar radiation, which would be a cooling aspect. So it brings it back into equilibrium. That's just one example. We could look at foxes and hares and any number of things in nature, but I'm just trying to get the positive and negative feedback loops there for you. Now, these last few things are to leave you with a smile on your face, and I hope you see it this way. Back when Kansas was trying, and Delaware were trying to, school boards were trying to get what was creationism taught as science within science books, using a book of pandas in man or something like that. I can't remember what it was. This was a legal battle, by the way, that was eventually shot down. But to say that creationism should be taught hand in hand with the theory of evolution. And so when I found this when it came out, I thought it was really kind of funny because they had changed creationism to intelligent design. And I get it. What I'm telling you here, though, is this. You can be as religious as you want, but we're going to be working from the framework of, again, data, science, testable, provable, all that kind of stuff, the scientific method, not something else. Okay, and so this one also came out around that time, and it was one of the things that individuals who didn't like. They were fine with gravity, they were fine with plate tectonics. It's just they didn't like that, you know, somehow that evolution somehow took God out of the picture. Okay, well, you know, if you're looking at external unexplainable forces, that would be alchemy. Phrenology, if you don't know, is quack science about the shape of this kind of goes into the Aryan race kind of stuff. Even that magic, that's a famous statement by, I think it was, what was his name, science fiction writer Asimov. Any sufficiently developed technology is indistinguishable from magic, I think is how the quote went, which is awesome. And it's true. I don't know how the computer works, and I certainly don't know how E equals MC squared works, but for those that do understand it, and the theory of relativity, go to town. But we're not looking at if you're a Leo or a Gemini here. We're looking at true astronomy. If in our first couple of chapters, you're going to see this in planetary stuff. Okay, I even covered it in the first lab, looking at perihelion and aphelion and how the calendar works. So guys, get ready. We're going to look. We're going to have fun with this. I hope. I will tell you what is truth and fact. I will distinguish between my opinion when it pops up. And I want you to come out of this class not repeating what I say, but to have a good foundation in earth science with weather, climate, landforms, and biogeography, among many things, that you can form your own opinion, because we need new opinions and new solutions and new scientists to solve for the problems that we continue to face as a species. All right, I'm done with this introduction, and I'll see you in the next lecture. Take care. Bye.